Good morning mga lagan. So we will continue with our discussion on loading calculations. So this video will be part 2C of the loading calculation. So we are done with we were done with did load and then live load, snow load with snow drift calculation. So that is part 2A. And then portion of the funding load is also part of part 2A. And then the latest video we have is the part 2B, which is the second half of the funding load. So we are done with all the gravity loads. This one. Now we will start calculating for the lateral load. So that is the wind load and the seismic load. So if we still have time, we will do the seismic load together with the wind load. If not, then it will be on the next video. Because last time when we did the second half, it's just the second half of the funding load, but yeah, it already took me almost an hour to discuss just the second half alone of the funding load. So I will try, if we still have time, we will discuss the seismic load together with the wind load. But we will do the wind load first. Now going back to our floor plan, so we'll just create a new page here, and then we will insert picture from file, and then design floor plan. So this is our floor plan. So this is a one-story wood frame building, and then the the building size is 80 feet. Oh, this is the floor plan. This portion here. So this is the floor plan, and then this is the elevation. So to calculate for the wind load for this structure, um, this will be if you are designing the shear wall, the lateral force resisting system of your building. So you have your lati sorry, you have your lateral force resisting system. So, for example, in concrete building, so your lateral force resist main say if it's main wind force resisting system would be it's either because concrete is a rigid structure, so you have a moment connection um, between beams and columns, or you can have a shear wall, like concrete shear wall, and usually it is the um, elevator shaft that is used as a shear wall. So for wood frame, you can also do a like if you want like a masonry shaft or a concrete shaft for your shear wall, but it's common to use the shear wall, like wood shear wall, instead of like a single like a elevator shaft in the middle of your um, structure. But if you have some projects like heavy timber construction, then you have like posts and beams, and then you have huge like curtain walls around your structures, and then there's no room for shear wall. Then another option is cross bracing. So you have cross bracing or any type of bracing. You have an chevron or um, inverted or no the knee bracing. So you can do something like that. But for regular or light frame, because this is considered a light frame building, which is just wall studs and then beams and headers, unlike heavy timber construction where you have like post like 8 by 8 or 10 by 10 dimension number, or sometimes like a glue lump post, and then you will just have like a huge sometimes cross laminated um, floor diaphragm, and then transfer that to your elevator shaft as your shear wall. But for this one, this is just a regular light frame building where we use the wood frame, the shear wall as our lateral force resisting system. So to get the forces on your building, so basically, if we have this building, this floor plan, and then you have to calculate like how much force is acting at its wall in the, say this is y and then x axis, so along y and then along x as well. So going back to the Jabacos online design tools here. So we go in BC 2015. Let me just switch that one. So this one here loads in BC 2015. So again, I am using the Alberta Building Code, or the National Building Code 2019 Alberta edition, which is based from the 2015 National Building Code of Canada. So I'm using this one here in BC 2015. And then if we go with the Jabacos, we have here primary structure, and then walls, and then freestanding plates, walls, and billboards. So these three here are for the wind load calculations. So primary structure, this is if you design the whole structure, and then you will design the shear wall later on. And then the walls, this one figure 4.1.7.6b, that is the wind load specified if you are designing the wall stud. So the wind load for calculating the wood stud is different from the wind load using or you use for designing the primary structure. So in primary structure, you don't consider the internal wind pressure, and in the Woolstad, that's the time you would consider the um, um, interior wind load or wind pressure. So for example, this is your cross section of your building, and then this one here is your roof, and then this is your wall, and then this is your wall, that one. So this is if we cut section say in this direction, right? So we cut section there. So this is your wall, this is your wall, and then this is your roof. Say you have your trusses there. Now the wind load acting on your walls, like if our if the wind is in this direction, so we have wind pressure on this wall. This is if the wind is going that direction, this is called the windward windward, and then the pressure on this side at the back is called the leeward. So that is leeward. So the internal pressure is either away from your structure or away from the wall or towards the wall. So if you are using the negative internal pressure. So when we say negative, that is away from your wall. So if that's the case, you have here away from your structure, right? So that is away from your structure. This is negative. This is the negative internal pressure. So if you notice, the direction of this force is going to the right, but on the left, it's going on the left wall, it's going to the left. So it will just cancel out. So this internal pressure going out or going away from the wall, and then this also away from the wall, they are canceling it out. They are like opposite direction. Then same value because that's the internal wind pressure is the same value all throughout the interior of your structure. That's why internal pressure is not considered when calculating for the primary structure like the whole building. But if you design just, for example, if you design just this wall, this one here, that's the time you consider the wind from outside pushing the wall inward, and then this one, you will consider the windward as well as the internal pressure. So you add these two, and that is the worst case because the other condition, if you have the other condition, if you have the positive internal wind pressure, and if that's positive, that is towards the wall. So if that's towards the wall, that means this one here will be, or this positive internal pressure will be subtracted from your windward load, and that would result into a smaller wind pressure on your stud. So that's why you have to consider the worst case, which is if you have the windward and then you add the negative internal wind pressure because that is away from the wall, and then you have to add the value of the two. Unlike if you use the positive internal pressure, then it will be subtracted from your um, windward, which yields a smaller wind pressure. So like I said, that's why the when designing the whole system, the internal pressure is not considered because they will just cancel out. It's not because it's not there, but it will just cancel out. That's why it's not calculate. It's not considered in the calculation. So going back to our Java cost, so we will use because we are looking for the um force like wind force in designing our lateral frame system, which is a wood based shear wall. So we'll check or we will click this primary structure, and then this is Alberta, and then the location is in Grand Prairie. Let me check this one. So Jabacos again, and then this one primary structure, this one, and then input your location. So like I said, if you don't know the project location or if the project location is not in the selected locations that is in the Jabacos database, then you just have to find the specific um what we call this one specific climatic data in that particular location. For example, I'm in Alberta, and then for the location we have Grand Prairie, and then there is no Grand Cache in the database from Jabacos. All you have to do is the you just go to the Alberta building code, and then And then the climatic data is on page, like the table is 615, page 615. So from here, you will have information of not all towns and cities, but um, for example, here. So we have information for um, Grand Center, Grand Cache, and Grand Prairie. But this Grand Cache and Grand Center, like the climatic data, it's not included in the Javacost.com primary or location like database. Then all you have to do is just look at in the climatic data from the National Building Code, and then you will see all um, the different location there. But if ever geomatic or what's it called, like the location of the or the rating location of your project is, say, small in a small village, and then you cannot find look or village in either Jabacos or in Alberta Building Code or in the National Building Code. All you have to do is just, usually what I do is I will just find the location of the project, and then I will see the adjacent towns or cities, and then whichever city or towns that has the biggest wind load, then I will use that city or that wind load from that city or wind pressure from that city. So it's more of a judgment call. So I don't know the other designers or engineers how they would do it, but in my case, I will just, for example, here in Grand Prairie or in the county of Grand Prairie. So if, um, for example, between Sixsmith and Grand Prairie, there is a another um, town, uh, Claremont. So Claremont is between Sixsmith and Grand Prairie City, the city of Grand Prairie. But those like city of Grand Prairie and then Claremont and Sixsmith belongs to the county of Grand Prairie, number one. Then what I will do, I will probably show you in a map, so it is clear. Let me just um, I will show you in I will show you um in a map. Clear. So this is Claremont, and then this is the city of Grand Prairie here, and then Sixsmith is right here. This one for wind load, I think they are Sixsmith and Grand Prairie is the same, but in snow load, Sixsmith is higher than the city of Grand Prairie. So that's why when I if I have say a project in Claremont, I will use the snow load from Sixsmith because it is higher than the one in Grand Prairie. So we'll see that in the um, in the climatic data table. So Grand Prairie, if where is it? Grand Prairie. So Grand Prairie, this one, this is the ground snow load, 2.2 kPa. But in 6 Met, it is 2.4. Where is it? This one. See? It's 2.4. So if the project is in between two towns or cities, and that project location is not in the table, all you have to do is just select the biggest between the surrounding areas where you can find a climatic data. And then for wind load, hourly wind pressure, this one, I think they are the same. 6 Smith is 0.43. Yeah, the same. 6 Smith is 0.43, and then Grand Prairie is also, excuse me, Grand Prairie is also 0.43, this one. But for example, if your location is in between Grand Prairie and Grand Cas, these two here. So if that's the case, Grand Cas is 0.45, 0.43 for Grand Prairie, and then if the location is between the two, then I will use 0.45. That's what I usually do. Maybe other engineers would use like will do some kind of interpolation, so average between the two, 0.45, or that just do linear interpolation. So if it's closer to Grand Cas, then maybe it's uh, 0.44, 0.445 or something like that. And then if it's closer to Grand Prairie, then maybe 0.435, something like that. Or you can just simply get the average. But what I usually do is I will use the biggest value between adjust or surrounding locations. So it's more of a judgment call. So it depends on you. So if you're the designer, then if you think that that's the or the value that m- makes sense on your location, then go for it. So at the end of the day, you are the engineer of record, so you are responsible of what you are doing. Um, and of course, if you use the biggest load between the two, then you are designing it based on the worst case condition. So that's fine. So going back to Jabacos, and then we'll continue with the. So this is Alberta, and then our location is Grand Prairie, and then the importance factor. This is a restaurant, so I'll just say okay, it's just normal importance. And then the terrain, um, well, it is a restaurant. I don't. I mean, there are instances that you have restaurants in the middle of nowhere. But we'll just say okay, this restaurant is within the city boundary, and we'll just use rough terrain. So this terrain, condition, open terrain, and rough terrain. Actually, in the building code, there is another one, the intermediate terrain. That's in between rough and open terrain. So if you go to the um, this is the what we call this one supplement for the part 4 of the National Building Code, the commentary. So you can download this one. That's the good thing. Before we have to buy the actual like hard copy. Actually, in the office, we still have the copy of the 2010 commentary. So it's more like a supplement to the building code, and then it explains all the terms and even have examples how to calculate just for the part 4 of the building code, like just for structural. So if you Google the um, NBCC commentary, so you will see here structural commentaries user guide 2015. So if you click on this one, and then like I said, if you want the soft copy, $45, you have to buy this $45. But the good thing is they have a free PDF version of it. So download that one, this one here. View the final version. I already downloaded this before. Then this is basically what the PDF looks like. So this is um, Structural Commentaries User's Guide in BC 2015, Part 4 of Division B. So this Part 4, that's the structural portion. of the building code. So going back to the different terrain, so this is the exposure factor. So this is the example of open terrain. This one, um, this one here. We'll see if we can zoom this. Okay, so this is example figure one or figure I-2. This is the open terrain under the static procedure and of exposure A under dynamic procedure. So that's what an open terrain looks like. So it's open field. So if you have projects, if the project is in like in um like acreage or in the rural area, then it might belong or it might be under the open terrain exposure. And then this is the uh, open and rough. So this is this portion here, this one, this below here, this is the rough. So basically, this is just showing between the difference between the two exposure, the open. The portion above, that's the open terrain, and then the one below is the rough terrain. And then where is the? So this is the example of a rough terrain. And then where is the explanation for intermediate exposure? Let me check. There is a it should qualify the distance. I think it's 1 kilometer. If it is 1 kilometer, let me check. Uh, I don't know if it's discussed in the Alberta Building Code. Just wait, I'm looking for the definition of the um, intermediate terrain. Where is it? I can't find it. But anyway, the definition basically is, for example, this house here, this structure here in the middle, this one, you could argue that this is between an open terrain and a rough terrain. So it is maybe 300 meters from the rough terrain exposure. So you can use the intermediate exposure on that one. Intermediate, but it's not in here in the option. In the building code, there is the third exposure, which is the intermediate. And then if you want, you can if you can optimize your design, you can use the actual factor for that one. So anyway, so the reference height in meters. So this the definition for reference height. It depends. If it's a gable roof, and then that would be from the grade level, from the grade to the mid height of your roof. If you go back to, by the way, there are three procedures in designing a or calculating for the wind load of a structure. So the first one is static, and then the second one is dynamic, and then wind tunnel. Wind tunnel are for skyscrapers. You don't use um, wind tunnel for one-story building. I mean, you can, but it's not required. So, and in dynamic, there is a like height requirements before it will fall under dynamic analysis. So there is a definition here, like this one is like procedure described in 4.1.7.3, and then dynamic also 4.7, 4.1.7.8, and then this is the criteria. So typically for like just two-story, three-story building, it will fall under static analysis. I mean, you can do dynamic analysis if you want, but the minimum requirements for that one is only static. So before when you design, before you decide to use the dynamic analysis, or before it is required to use the dynamic analysis, this um, clause here 4.1.7.2 dash 2, these are the classification um, or criteria if the structure belongs or requires a dynamic analysis. First is your lowest natural frequency is less than 1 hertz and greater than 0.25 hertz. So, and then this one, I mean, we will do the sample calculation for this one, but we will talk about this one first here. But this is just like a based on the dimension of your structure. So if the height is greater than 60, it's automatic that it requires a dynamic analysis, 60 meters. So if the average, say, average floor to floor is 3 meters, then this is 20-story building. So that's about mid-rise structure. And then if the height is greater than 4 times its minimum effective width, it says here minimum effective width. That's why it is termed as effective width, because if you have two different height, like you have a steep roof similar to what we have the main structure, which is 20 feet high, and then the vestibule. It can fall under this. Um, then you have to calculate like the effective width. So if this is just like on our example, disregarding the vestibule part. So if the height of the structure, so our structure is let's open another page. So our height is 20 feet, no? That is um including the parapet. So for the sake of discussion, we'll just consider everything as a roof height. So for height of the building. So if your height, which is 20 feet, your height, if height is greater than 4 times the width of your building, which is between 80 and 60, we have a level with normal to the wind direction. So if the wind is going in this direction, if you are analyzing this condition or load case, when in the X direction, so you will use the 60 feet. So of course, our structure is the height of the structure is just a third of our width. So for sure, this will be under. You can use an static uh, procedure on this one. If, ev- I- For example, if it's the other way around, your structure is or your so your this is your floor plan. This is only what um 10 meters by 10 meters, and then your height is 40 meters. So 4 over 10 is 4. I mean, you are in the limit. So I think in this case, you have to design it using or analyze it using the dynamic procedure. It's within the boundary, the maximum. I mean, technically you can still use the static, but it is right at the limit for the dynamic procedure. So it's better to design it using or analyze it using the dynamic procedure. But in our case, our height is it's only a third. Our height is only a third of the width, so we're good with the third criteria of the um, building code for the dynamic procedure. And then, of course, our building is 60 meters, so that's um, that's a lot, uh, or that's really high for the required height. I mean, our building is only 20 feet, so that's about 6 point something meters. So that's way that's only like about 10% of this uh, height limit. So we're good. So we can use the slide procedure. But even if our building is less than 60 meters in height, and then our height is less than four times the width, or greater than four times the width. No, even if the building the height is less than four times the width, but we will calculate this one, and then if it turns out that the frequency of your building is between these two values, 1 hertz and 0.25 hertz, then you have to use the dynamic procedure. It means your building is really flexible. So to determine the fundamental period of vibration, so you will use this different equation here. So for still moment frames, you have to use 0.085 times um, the reference height each N, and then raised to 0.75. And then for concrete moment frames, and then zero point 0.1 N for the for other moment frames. And then for shear walls and other structures, we will use 0.05 times each N raised to the power 3/4. So we will use this one, 0.05 each N. So going back to our calculation here, we will just erase this first. So the period calculation is 0.05 times each N, then I will just use 3/4. It's basically the same, 3/4 or 0.75. So this is the period. Now our each N is 20 feet, but this is in meters. You have to use in meters. So 20 feet, uh, how much is that in meters? 20. Points, 6.1. 6.1 meter. This is the height. So therefore, our period is 0.05 times 6.1, 3/4. So that is 0.05 times 6.1. So this is 0.19 seconds. So that is our period. F is equal to 1 over period. So frequency is 1 over period. So therefore, this is 1 over 0.19 seconds. So therefore, your frequency is 1 divided by 0.19. This is 5.06 hertz. So it says here, if the dynamic analysis or natural frequency is less than 1 hertz, this one, and greater than 0.25. So it is, if it is between 1 and 0.25, then you have to consider dynamic analysis, or you have to use the dynamic analysis. But our frequency is 5 hertz. Then we are good. we can use the um, static procedure. So um, we will see what's the period of vibration that would require a dynamic procedure. So we'll use the 0.25 hertz. So we will reverse the calculation. How much? What's the period before you can consider, or the period of the building that will trigger a dynamic analysis? So we will use um, the same formula. This is F is equal to 1 over T. Therefore, T is equal to 1 over F. And then the frequency that will trigger a dynamic analysis 0.25, 0.25 hertz. No, not 0.20. 0.25 hertz and then 1. Therefore, our period is 4, 4 seconds. So if the period of vibration of the building is at least 4 seconds or more, then that's the time, or 4 seconds, then that's the time you would need a dynamic, or you will use the dynamic procedure. So we will use the Jabacos. We'll see if we will arrive at the same answer. The period of vibration T is 0.19 seconds. So going back to Jabacos, so again, our reference height for internal exposure, 6.1 meters, as well as the external exposure, 6.1 meters. And then internal pressure category. So this category, uh, category 1 is if your building is like closed all the time, like an apartment, so that belongs to category 1. If it's a shop where it is open but is closed during a storm, then that is a category 2. And then category 3, usually those structures, like I said, with like at least one side open, like a shed, it is open, then that will belong to category building. So the definition or the explanation of these categories also can be found in the commentaries, National Building Code commentaries. Let's see here. So category 1, this category deals with building without any large or significant openings. And then building category 2, this category cover buildings with in which significant openings, if there are any, can be relied on to be closed during storms. So like I said, if you have a shop, so you have large overhead doors, and then this would assume that during a storm, like a windstorm, you close that overhead door. So that's the condition. Um, that's why most of our projects are like shops anyway. I always use this category, category 2. This is for like with large openings, but the door must be closed in the event of a storm. So that's the condition. Otherwise, it will be under category 3. So this category covers buildings with large or significant openings through which gas are transmitted to the interior. So example of such building include those with a permanently open door or window and shed. See, shed with one or more open sides. So, and then it says here, post-disaster buildings should also be treated as category 3 in order to achieve a high level of reliability. So, if it's post-disaster building, it's automatic, category 3, and then you have to use the importance factor for a post-disaster building, which is really high. Let me check, or 1.5, this one here. Let me check. Importance factor post-disaster, 1.25 for wind load. If this is a post-disaster building, normal, just 1. So, like I said, this this is a restaurant, and then of course the only door that will open is of course the entrance door, and then if you have a delivery door outside or on the other side or whatever, but it's always closed. Then it's you can use for that particular example, like our example here, it's a restaurant, so we can use the category one on this one. So if you look at the period, um, no, not on the seismic um, or wind load. You go to the seismic. So building this one here. So user values, because the period of vibration that is critical in the seismic analysis, but that is also the criteria when you design for the wind load. So Alberta, Grand Prairie, and then for site class, we'll just use class B for stiff soil, cohesive soil like clay, stiff clay, and then importance factor normal, and then this is a, now we selected the 0.05 each end raised to the power of 3/4. That's for shear walls. Then we will use timber, and then ano, shear wall, and then nail shear walls wood based. The other option is this one if you have a shear wall where your sheeting is a combination of a plywood and a gypsum. So we'll just select the nailed shear walls wood based without the gypsum, and then the height is 6.1. If you have different calculation, then you just input the period there. If not, that's why it says here optional, because if you leave this blank, then the program, like the Jabacos program, will calculate the the period based on your input here. So the period should match our calculated value, which is this one. Um, it should match the 0.19 seconds. This one. Uh, it should match this value, 0.19. So going back to Jabacos, see this one here. TA computed. It is 0.19 seconds. So that equates, or that is the same as our um, calculated value. But basically, this Jabacos is based on the code. So and then we input that it is a wood frame, wood shear wall for your framing system, and then 6.1 meter height. So the period is 0.19 seconds. So we meet the criteria to use the static procedure. So we will use the static procedure, this one. The one in Jabacos, this one here, this is a static procedure. So again, so we will input the data. So project, this is one story wood frame building. And then designer is Lagan at work. And then date is already there. So province, Alberta. Then location is Grand Prairie. And then return period. So if this is a permanent structure, then you use the 50-year period. But if this is like a seasonal structure, you only erect this during summer maybe. We had one project where it is a like a cover all building, like a fabric building, and then we were asked to design the foundation. The foundation is just a concrete blocks. So um, the wind calculation for the wind for determining how much is the lateral force on your block, like a kick on the structure, then we use the Q10. This one, 10-year occurrence. That's the minimum. So like I said, this one is a permanent, I would say, considered permanent structure. It is designed until what's the lifespan of the building. Um, Wood frame here. Unlike in from where I came from, like in the Philippines, our wood. If we have a timber structure there, I don't think it would last like 5 or 10 years. It will be infested with termites and get easily rotted if it is exposed to moisture or wind. No, water. We have like storm all the time, so we have to rebuild our like hut or like small houses. But here I've seen like structures from the 1940s, like even permanent wood foundation, like residential houses or like a small like farm buildings. It's been here for like since 1940s, 1950s, and it's still like condition is like structurally is still considered like you know good. So because there's no termites here, um, that's the good thing. That's why you can easily just use wood frame here. But anyway, so again, this is rough terrain. This is a restaurant, and then we assume that it is within the city limit. So reference height is 6.1, and then height for the internal is 6.1 as well. And then roof pitch. So this is a flat roof, so we use 0. And then internal pressure category 1. So these are our values here for different portion of the structure. So this shaded portion, this is 1E. Then you will just use this here, 1E, 0.35 UPA. And then on the other side, the wind. So 1A and 1, that is considered as your windward. So if you, I mean, when you analyze this one, you have to use the plus and minus sign of your wind load. So your wind load could go like from right to left, and then another combination. If you use, for example, software like design software like SAP, and then if you have a load that is assigned to a wind load, when you generate the load combination, it will automatically um, include a plus wind and a minus wind. So it's automatic. And then when you apply or when you calculate for the envelope, it will calculate whichever the is produce the worst um, possible scenario or like biggest reaction. So on this one, 1E is this one is assumed to be our windward, and then 4 is assumed to be our leeward. So if you have a regular structure, for example, um, we'll have another page. For example, if you have a like an irregular structure, something like that one, and then if the if this is your windward and this is your leeward. Now, in going in this direction for the windward, the resisting walls are this two, this one. Although if you run a drag strut here or drag truss, this one, if you have a drag truss in this location, then that's the time you can actually use this wall here. But without the use of using like a drug truss, then for the windward, the only acting wall or resisting wall are these two here. But if the wind is on the other direction, if the windward, when you assume or we realize that the wind is coming in this direction, and then this now is our windward and this is our leeward. Now for the leeward, you will now have three walls acting. or resisting the load. So that's why you have to, for irregular structures, it's better to run like um, leeward and windward in each direction. And I mean, in our example, of course, I made it like a square, so it's a or rectangle, so it's a this is just like a basic design anyway. So at least the idea on how to design this building, it will be discussed. But these are just like irregular structures, and maybe in the future we will deal with this one. But for now, we will just assume the rectangle layout. So um, going back to our Jabacos, so 1E is 0.35, and then 4E is um 4E is 0.17. So we will interpret that result in our floor plan. So let's insert again our floor plan. So this portion here, this is our um 1E, and then the rest would be um and then the rest would be add pen highlighter, we use green. So the rest would be under 1. Um, this will be 1, just 1. And then on this side, on the leeward side, this one would be 4A, and then the other side or the rest would be 4, this one. So the wind pressure on this one would be 1A, and then the direction, if you look at the if you look at the if you look at this one, so 1E is 0.35. Where's So 1E is 0.45, and then what we call this one, the like 1 is 0.23. So 0.35, 0.33. So in the floor plan, so you will have in this direction within the boundary. So this is 0.35, and then how much is the point? And then this one here for 1 is 0.23. So that is windward, like going up direction. And then on the other side, 4E is negative. So it's a negative value. 4E is 0.24. So negative means it is um, away from the wall or away from the structure. So the positive 4A is towards the building, but since the value is negative, so that is away from the building. So it means it will be in this direction. It is suction. It will be pulling your building um, or pulling the walls away from the structure itself. So in this case, you will add the value of the two to get your load. Now, what I typically do when I analyze this one, because in this case, this is your load application, and then this diagram will produce a rotation. It will produce a rotation here. I mean, this is the proper way. It will produce a rotation, And then, although the wind is going in that direction, because we have this rotation, we have a load acting on this wall. Because it will be like, for example, if this is our structure, and then if you have like a direct load, because right now, with this bigger value, 0.35 and point 20, I think 0.25, was it 0.25? The centroid, or the center of this load, if you get the reaction, it will be offset from the center of mass of your structure, or center of gravity of your structure, whatever is term you use. I mean, it's interchangeably. Yeah, you can use interchangeably the center of mass and center of gravity, as long as the gravity is constant. Of course, if one end of your structure is on Earth and then the other one is on the moon, of course they have different gravity. Then you cannot use the center of, or in that case, the center of mass is not the same as the center of gravity. But we are just the center of gravity is constant, so that's why we'll just use either center of mass or center of gravity. So right now, what will happen is the the um, the load, or the resultant of the load is offset from the center, because this portion here is higher than the one on the right. So if this is your center of mass, and then you have your load like a offset, what we typically do when we design like any, it's not like a column or something. Remember, we will move that wall or that load to the center by a distance e. That's the centricity, and then you will counter that one with the same load P. So if this is P, this is also P. So this one here and this one cancels out, so it's the same. So as if this one, this load is the one acting along. So since we have an eccentric load, our total load would be, for our total, we have a rotation, which is because of this combination, a couple. So we have this one, this will equate to, uh, so that that diagram would equate into a load at the center, and then you have a rotation like a couple, which is your M. This is your M. M is equal to P times the eccentricity. So if that's the case, so for the lateral load alone, for the lateral load, you will have reaction from here, like on this wall, which is opposite in the direction. But with the application, or with the addition of the moment load, that rotation clockwise will result in a reaction counterclockwise. So we will have a counterclockwise um, reaction, or like that. So again, what will happen now with this diagram is, even if our load is only acting along x direction or y direction this time, like up and down, like on the plan view, it is still um, contribute a lateral load on the perpendicular walls, this one, because of the rotation. And then if you notice on this one, on this side, you have the, say for example, if this is 100, if that is 100, then this yellow is 50. If it is just like a if the load is regular and then it is acting at the center, then therefore our reaction is only 50. But with the addition of the rotation, then you have this reaction would be added to your 50. So maybe you will have it depends on the eccentricity. So maybe you will have, instead of 50, you will design this using, um, if you add the counter reaction from the rotation, instead of 50, maybe this is 60 kilonewton. So we don't know. It depends on how much is the eccentricity. So, and then on this one, since this is in opposite direction, so maybe this is now, instead of 50, you will design this 40. But but the wind load can be in different directions. So on this one, we only assume that it's going up. But what if the wind is going down, right? So what if the wind is going down? What will happen to the reaction? It's the opposite. So this is now the 60, and this is now the 40. That's why when you design, you have to assume the worst case condition. So it's either going in this direction, uh, going up or going down. So calculating for that's the envelope, the maximum force from your envelope would be 60. Because if the wind is going down right here, this is the 40, this is the 60. But if the wind is going up, this is the 60 and this is the 40. So you always use the biggest value, which is 60. So when you design this wall, so when you design this wall, uh, highlights. So when you design this wall, instead of just using the 50, because the horizontal load is 100, you have to consider the eccentricity. That's why you will design the load by, instead of 50, you design it using the 60 kilonewton load instead of 50. So you have to make sure that you consider that one. I mean, based on this diagram, there will always be a rotation. That's why also in the code, it says there, like, you design the structure based on the worst condition, including the effect of eccentricity, like rotation, just because of this one. And in my case, what I will do, um, if it's just a regular structure, what I will do is whatever is value here, 1e, on this width here, there is a calculation for like how much is this width, and then I will use the same load here, and then I will apply it like symmetrically. So basically, my wind load will be, instead of our diagram is like that. No. Um, if the structure like is too close, it's, I mean, not too long. Like, I mean, the length of the structure is um like, say, 30 feet or 40 feet. This is what I usually do. But if it's like 150 feet long, then that's different story. You have to do like the proper way. I mean, um, I compared the results of the two before. Like if it's just like 30 feet, 40 feet, the difference is not that much. So I mean, this is the recalculation. So I will just use. I mean, it's up to you if you will use the same procedure as this one. But for smaller buildings, I will just use. If this is the wall, what I will typically do for a small building is I will apply the wind here, the bigger one. Then I will do the same on this one here, and then the smaller wind pressure in the middle. And then so I will just analyze the structure like just one calculation. I don't have to consider any rotation. But if the building is really long, like 150 feet, 100 feet long, or even like 100 feet long, then you have to do the proper way, which is including the um, uh, rotation that is produced by the eccentric load. So again, it's your call. It's judgment call. So it's up to you. But like I said, this is what I usually do for small buildings. And besides, the the criteria for the or for the width of this one here, if it is like a stud, it is discussed in the building code. I Let me check if I can find it. So that is distance y, and then on the end wall, this one with the this is case two. Case two is the wind is parallel to the ridge, and then case one is perpendicular to the ridge. And then if you want to calculate your own like wind loading, you can do so. You don't have to use the Jabacos, but why would you? I mean, at first I did the manual calculation, and then that's what I usually do. When I, for example, if I do like a spreadsheet myself, I will do a parallel calculation using the software or the tools, online tools or software, whatever it is. Then I will do a manual calculation and then compare the result. And then because in any software they're saying like garbage in, garbage out. So um, if unlike like those like tried and tested software, that's fine. But if it is new to you, just do some due diligence. Just do some manual calculation, then compare the result. And if you are confident that, for example, in this case, like Zapacos is good, like all calculations are like okay, then I I will use it. Um, yeah, ever since I've been using Jabacos in my calculation. So yeah, so there is a calculation for how much is that distance y and um, right here. So this is the criteria. Calculate for the z. It's pronounced as z here. So in zone with z is the lesser of 10% of the least horizontal dimension and 40% of the height, but not less than 4% of the least horizontal dimension or 1 meter. And then y, distance y, where is it? Oh, here. In zone with y should be the greater of 6 meters or 2 times z. So whatever is the value of your z, multiply it, and then choose the between whichever is bigger, 6 meter or 2 times the z values. So like in my calculation, I always use like 20, 20. I mean, it's a small building. For a small building, 6 meter always governs in the calculation. Even in I have a spreadsheet here. Let me just so on this one, so I have let's check. So this is Alberta, and then Grand Prairie, Grand Prairie, and then this is normal. So this is a like this red values is if this is a user value, then I will input this one. So if I select user values here, it will use this value, whatever is in these values here, the same as this one. This one, this is linked. This uh, black text is linked to the climatic table. So if you select this one here, whatever selection, it will automatically adjust. But this one, if this is a user input, and then terrain is rough, and then topographic factor city 1, and then exposure category 1, and then longer dimension, this is 80, and then this is 60. Building eve height is 20. Oh no, this is my old spreadsheet. So this should, because in my new like in my new update, um I have the option of if this is imperial, like the input is imperial or metric or SI. But this is 18.29, and then this is 23.38. Then roof cladding, composite, overhang, no, single gable. This is flat or single slope, slippery, no, composite or cladding. This cladding, I just added this option here. So because I made this one to um determine, for example, like I said before, like when we do pre-ins building, our scope is typically just the foundation, and then sometimes the steel building is still under bidding who will supply it, but the contractor needs the foundation already for building permit submission. So what I will do is I will do a like a mock-up calculation of the frame itself, as if I'm the one designing the rigid frame, so I can get the reaction. So I will do the analysis that the pre-ins building supplier will do, like calculate for the dead load, live load, snow load, and then analyze the structure. And then what I will do is, from my calculation, I will just add usually 10 to 15% extra or additional, and then that would be my or extra 10 to 15% of the reaction from my analysis, and then I will use that as the load for the design of the tile, because sometimes the general contractor is not selected yet, or it's already selected who is the general contractor, but the building supply for this Prince building is still under tender. So um, and then the contractor wants to start the process of applying for a building permit, and so I will design the what we call this one, the structure, get the reaction, and then for the components, sometimes if the architectural would ask, like, what's the minimum Portland's depth on this one, then I will use this calculation, like a preliminary, like a calculation to determine what's the possible, because I don't know like what would be the final output from the pre supplier. At least we have an idea, and then we can say, okay, at this particular loading at this span, you have to use minimum 12 inches of Portland's. So I can calculate also for the weight of the entire building for the seismic load calculation. So composite is basically, it means that the internal pressure, this is if you are designing the cladding, and then the internal pressure is acting on the same cladding. For example, if your wall, I only added that option because if this is your, or this is your, not for pre building, this is your girts, right? This is your pre-ins column, and then you have your exterior cladding, and then you have liner, interior liner as well. If this is non-composite, your wind load is only acting on the exterior cladding, and your interior wall or interior pressure, internal pressure is acting on the liner, interior liner. So when you design the the interior liner, you will only design it based on the internal pressure. And then for the padding, the metal padding, you will design it only for based on the external wind pressure. But of course, when you design the girts itself, so when you design the girts, when you design this one, the girts, then you have to apply the true load, because the element that is supporting the internal pressure and the internal interior liner and the external or the exterior cladding is the same. But when you design the cladding and the interior liner, if it is non-composite, then it should be designed differently with using different loads. But the composite, if this is your cladding, and then your liner is right here inside, and it is one structure, one single element, then all your exterior and interior pressure will be acting on that composite cladding. So um, basically that's how that's the reason why I added this option. So in my output, I can separate what's the internal pressure. For example, this one here, in wind internal pressure or liner sheet. So this is only taking into consideration the internal pressure on your internal liner. But if this is composite action, then you don't consider the what is one? You don't consider the or you consider both external pressure and internal pressure. And then in the calculation, also, I have here two tables for the result. I have the wind pressure for non-composite cladding, and then I also have the composite cladding. If you notice, I already added here for the CGCP. I added the internal CGCP, this one here, and then of course this one for non-composite. The reaction is a 11.32, oh, 11.32. But if it is a composite action, the wind pressure is now 13.21. So because this is for wall cladding. For composite, then like I said, you consider the internal pressure. Wait, it's already 1.5 hours. Jesus. Um, I will just continue on this one. But definitely the seismic calculation will be on separate video. So again, so for the primary structure, so I have here the in-zone distance. So like I said, Z, this is the calculation. Z is 1.83, and then Y is the greater of 6 and 2 times Z. So 2 times Z is 1.83 times 2. So that's only 3.66, which means the Y value, the governing value is 6 meters. If it happens that the Z is, say, 4, and the 2 times 4 is 8, then should be 8, not 6. Because you have to select the greater between the two. So, and then this one, 2E, this one, 2E, is the uplift pressure on your, what we call this one, on your, um, uplift pressure on your roof. So, it's not typically also considered during for the primary structure when you analyze for the lateral frame resisting system, because the for example, you have a if it's a flat roof, if it's a flat roof, so like I said earlier, the internal pressure is this way, right? And then it will cancel out. And then what happened with the internal pressure is this is upward, but we are only calculating for the lateral. So that's why this is not included in the lateral analysis. But when you design for the shear wall itself, like when you starting to design the shear wall, or you analyze the anchor for your trusses to the template, then that's the time you will you will include this value here. But for lateral, like lateral, um, of course, it is perpendicular to the plane of your load application. Um, that is not included in the analysis, because like summation of forces along y, this along x, but this suction is along y, then you will not include that one. However, in a roof or a slope or gable roof, most of the time the wind pressure is acting this way. If you look at Jabacos, we have uh, 2E and 3E. See, 2E is negative zero point 0.6, 3E is negative zero point 3. It means it is away from your structure, the direction of your wind. So it's upward. And most of the time that's the case, it's upward. So far I've never designed a structure where the result of the wind pressure on the roof is downward. So far, I mean, we'll only use designing like small building. I don't know. I haven't tried designing structure where the the specified wind pressure on the roof is downward. So this one, so if you resolve this, so this is perpendicular normal to the roof surface. So what will happen is it will have a, of course, horizontal component and vertical component. So again, the vertical component, it will not be added to your lateral calculation because when you sum up forces along horizontal along x, then of course that is along y. You won't include that one. And then on the other side, you have also a horizontal and vertical. So this vertical again, disregard that one. The horizontal, this is in this direction. This is also in this direction, right? So although this value here, this leeward is always smaller than the windward. But this direction, this orientation of the load, this is if the if the wind is going in this direction, because that is the assumption. So this is the windward, and then this is the leeward. Going the force is going in that, or the wind load is going in that direction. Now the value of this leeward component is always smaller than the windward component. So if you sum up these two, you have a negative a net wind force going in that direction, which is opposite to your wind force direction. This one going to the left. Now, what will happen? This one will technically be reduced because of this net wind force. But we are designing this for a worst case condition, and we don't want this. I mean, technically, this is should how it should be done. But in my practice, I'll just completely neglect that one. I will just use this one, this wind value. And then by the time when I design the shear wall itself, and then if, for example, you have hold down, say H2 and H4, say I don't know the actual capacity yet, but for example, for the sake of discussion, this is 5,000 pounds capacity, and H2 is only 3,000 3,500 pounds. For example, the actual uplift for the anchor is 3,510, and then H2 is only good for 3,500. So I am short by 10 pounds. And I know for a fact that when I calculate for the shear wall, like the uplift, I neglected this value. This I neglected this net wind, which should be subtracted from your wind load. So in that case, I will just say, okay, we are only short 10. I will just use H2 instead of specifying H4. I mean, the price of these two is it's not much difference, but I mean, money is money. I mean, you have to save every penny. So, and the contractor would love that. So it's again, it's more of a judgment call now. But like I said, in my practice, I will just disregard this one. But I will consider that. I will take note of that net wind. That in this case, if there's a scenario like this one, although it already exceeded the capacity of H2, but since it is only small, then I will just use still the hold down H2. Like these are for Simpson. I'm talking about Simpson products. So I mean, it's up to you. If you subtract this one, that's why in lateral calculation for the primary structure, when you design the lateral force resisting system, um, I don't. I would say I would not usually include the pressure on the roof for this reason. So I mean, it's up to you. Like I said, this is judgment call, and my judgment would say, okay, I will just neglect this one, but I will take note of this value when I design the anchors, because that would also. I mean, also if you design for the hurricane ties of your trusses, like when you design for the anchors of your roof to your top plate. So what else is not covered here? Uh, blah, 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 blah. I think um I mean this is just like to show you how the wind load is calculated, and you can read more on the in the building code. But the actual analysis, like completing, like basically designing structure, we will calculate the wind load in later video when we start the analysis of the structure. But for now, I'm just showing you like how the wind load is calculated, and maybe if you have question, you can refer it in the building code. I mean, maybe it's different in other locations. I don't know. And other engineers also, I don't know how they analyze the structure, but this is how I do it. So um, if you have other way of calculating this one, you can comment on the in my YouTube channel or Facebook page and say, okay, this is how I calculate, and then maybe maybe I will learn from your procedure as well. Procedure. So for the seismic, we are already what 1 hour and 45 minutes. So we will discuss the seismic in the next video. We will just stop the recording here, the discussion. And again, please subscribe and press the notification bell so you will know, you will be notified once a new video is uploaded. And then bye mga lagad.